Over the course of my studies in theoretical physics, I've traveled across the continent and around the world sampling new ideas and tasting different answers to the questions of how and of why. And still, I find there remains a deep hunger which lives within me, a burning desire to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicists Podcast, and I'm Ben Tippett. And now, allez, physique! Dark matter. We owe the name to Fritz Zwicky, the groundbreaking astronomer who called his coworkers spherical bastards, because apparently they were bastards regardless of which angle you looked at them from. There's a constellation called Coma Berenices, which is Greek for Berenice's hair, and it's near the constellation of Leo. And in this constellation, there's a cluster of galaxies called the Coma Cluster, and Fritz Zwicky was looking at how fast the galaxies were orbiting each other. See, in astronomy, if you know that a celestial object is gravitationally trapped in a system, there's a relationship between how fast it'll move and the mass of the system. So Zwicky was trying to figure out how much mass there was in this cluster of galaxies. And there's an alternative way to figure out how much mass a system should have. From Hermetic philosophy, we have the phrase, as above, so below, and it turns out that this isn't such a bad axiom for studying astrophysics. For instance, the same universal law of gravity, which binds the moon in orbit around the Earth, can also be used to describe huge galaxies in orbit around one another. One thing which is true in our solar system is that most of the mass is concentrated in the sun. All of the mass of everything in the solar system put together is only about 1/1000th the mass of the sun. If this was generally true, then we should be able to determine how much mass there is in a galaxy by counting up the number of stars in it. So, there were two ways for Zwicky to figure out how much mass the Coma Cluster had. He could look at the velocity of each galaxy, or he could figure out how many stars there were in each galaxy, and figure out how much luminous matter the galaxies had in total. Zwicky found a problem, though. By looking at the velocities, he got a number for the mass which was 200 times higher than the number he got by counting up all of the luminous matter. But that's okay. He argued that the difference in the two accountings of the mass came from the presence of what he called dark matter. So that was 80 years ago, and to be fair, Zwicky's observation occurred only 11 years after astronomers began to agree that there were other galaxies beyond the Milky Way. So it's not so strange that Zwicky saw things that couldn't be explained. But the problem is that his dark matter has persisted. In almost every modern astronomical observation of galactic scale and beyond, we've seen evidence of it. So here's what we know. We know that it's not emitting or absorbing light. We know that every galaxy is filled with a ball-shaped distribution of the stuff. And we know that for every star in the universe, there's something like 50 stars worth of mass composed of dark matter. In our own Milky Way, there's something like 20 times more dark matter than regular matter. So, dark matter. How do we know it exists, and what the hell is it? Today, I'm pleased to announce that my guest is Kai Nagata. In 2010, Kai was CTV's Quebec City bureau chief until he quit his job as a reporter in 2011 because Canada's going down the crapper and the media's letting it happen. His open letter essay titled Why I Quit My Job made waves around the country, and I hope its message isn't forgotten. He works for the Taillis now, a multi-Murrow award-winning online news magazine. Hey, Kai, how's it going?
Ben, it's going great. I'm so confused already. I hope that the next little while I can unravel some of the mysteries that you have so delicately wound together like a ball of terrifying yarn.
Well, the yarn is terrifying, but I've got two fantastic experts today to help you unravel it. So, Kai, today I've assembled two of my best titanium physicists. Arise, Dr. Ken Clark.
Whoosh!
Wow, he came in on a breeze. So Dr. Ken did his undergraduate at the University of Toronto and his master's and PhD at Queen's University. He's now at Penn State working on Ice Cube. And now arise, Dr. Amanda Bauer. Nice. Dr. Amanda did her PhD in Austin, Texas, and she's currently a super science fellow at the Australian Astronomical Observatory in Sydney, where she studies galaxy formation. She also blogs under the name AstroPixie, and we'll post your blog link on our website. So, let's start talking about dark matter.
Okay, well, in addition to noticing that galaxies move around their clusters a bit quicker than what we can account for by all the luminous matter, in the 1970s, Vera Rubin also noticed that within individual galaxies there was a similar velocity problem, in that the stars in the very outskirts of the galaxies were moving entirely too fast for what we would assume they should be from just the gravity from the other stars within the galaxy. It's much different to what we see in our solar system. As you mentioned, in the solar system, the mass is dominated by the sun. And then you can calculate the velocities at which the planets move around based on how far away they are. So Mercury and Venus and the Earth feel the sun's gravity quite strongly and move very quickly, whereas Neptune and Pluto don't feel the strength of the sun's gravity as strongly because they're so far away, so they move very, very slowly around their orbit around the sun. So you would expect that in galaxies, since you look at them and you see a dense amount of stuff right at the center, you'd think the stars near the center would be moving very fast, and the stars at the outskirts would be moving very slowly. But that's absolutely not what we measure at all. We see that the stars on the outside move as quickly as the ones in the center. So this rotation curve describes how the velocity of the stars as you move out towards the outskirts of the galaxy. And we call it flat because the stars at the outside are moving just as quickly as the one on the inside. So there has to be something else creating gravity that's causing these stars to move so quickly that is not also producing light.
So it's kind of like you're playing tetherball, but the ball's just whipping around way too fast.
Exactly. So what is that tether? That's the problem.
This mysterious force of gravitational pull, is it occupying the same space as the sun, or do they overlap?
Well, we don't see that there's very much dark matter inside of our solar system, so it's not affecting each individual planet's gravitational field with the sun, but we do see it in the solar neighborhood. So it does look like stars that live nearby our sun are also moving a bit quicker than they should be based on the rest of the stars around. So it's all the way throughout our galaxy, and it extends even a bit beyond the edges of where the stars are in our galaxy, at least that we can see.
If things are orbiting around a central point, then I can understand that they would move at speeds relative to their own mass and I guess the mass of the thing that's attracting them. I guess what's crazy is that something in the solar neighborhood, as Amanda puts it, could affect the rotational speeds of things inside of, closed loops like the orbit of our planets around our sun. That's what's blowing my mind.
So what's going on here is that if you're orbiting around a loop, the speed at which you move around that loop will depend on how much mass is contained inside of that loop.
Mm-hmm.
So the more mass there is, the faster you can go.
Well, the more mass there is and how close you are together.
Yeah, that's right. So what happens in the solar system is all of the mass is concentrated in the center. So the farther out you get, there's no more additional mass in between you and the sun, but you're getting farther away. So the farther you are from the sun in our solar system, the slower your orbit will be. And so when astronomers did this type of calculation for the galaxy, what happens is as your orbit loop gets wider in the galaxy, it encompasses more matter. Okay, there are more stars. So they say, okay, if your orbit is very close to the center, you can count up the number of stars in that loop and figure out how much mass there is, and you get a fairly good description of how fast you should be moving around the thing. And then as you expand your loop wider and wider, you can still count up the number of stars inside that loop and try to figure out how fast you should be able to move around that loop. But when you do that, on the galactic scale, you count up all of the stars, and the stars that are moving on this loop end up moving much faster than they should be able to based on the number of stars inside that loop.
Gotcha.
So there's an invisible mass problem. Somehow there's a lot more mass inside that loop than there should be.
You're talking about the velocity rotational curves. I'm wondering, is that the only way that we can surmise the existence of this extra mass?
Well, there are other observational pieces of evidence. So one is called gravitational lensing. And this is predicted from Einstein's general relativity. When light travels across space and comes close to some gravitational thing, so to a galaxy or a cluster of galaxies, as a result, the light path actually bends. So if you have a galaxy that's directly behind some galaxy cluster, as that far distant galaxy's light travels around that cluster towards us, it actually gets bent around the cluster.
How much of a bend are we talking about? This has nothing to do with refraction, right? Like if you put a stick into the water and it looks bent, that's a totally different phenomenon from what you're talking about, right?
Actually, it's quite similar. If you look through, say, a window on a clear day, you might not even be able to tell that that glass is there. But if you have a raindrop on that window, if you look through that raindrop, you see that object outside completely distorted in almost like a ring manner. And that's essentially what the cluster is doing to the galaxy behind it. It's distorting that light in the same way.
Okay, yeah, that makes sense.
We were talking earlier about windows. Have you ever looked at really bad glass windows where there are visible warps in it?
Yeah, totally.
So as light moves through space, these warps are caused by gravity. So the more mass it is, the higher it's warping. And it gets to the point that if one of these really heavy objects passes between a far-off galaxy and us, it will bend the shape of the galaxy off so much that it will make the shape of this galaxy look like a donut. This gravitational lensing actually visibly looks like, something passing through a really, really badly warped piece of glass.
Which can be a good thing. Like if, you're talking about a bathroom window, you might want that effect. Maybe the extraterrestrials just don't want us to, look at their bits. It could be totally deliberate. It's just a way of throwing off our telescopes so we don't pry.
So that's exactly the point. And then using these general relativity equations, we can say, okay, we see this galaxy distorted in such a way, so there must be a certain amount of mass that's causing that bending. And in that way, you can calculate the total amount of mass and compare that to what the luminous mass is telling you. And we end up finding that these clusters have a 200, 500 times more mass than what we actually see and can count up in the starlight.
Huh. How else could we tell, or how else could we surmise that there's extra matter out there?
So, Saul Perlmutter was involved in a collaboration which won the Nobel Prize this last year, and he won it for an interesting observation. We can tell how fast far-off galaxies are moving away from us based on how the light that travels towards us changes color. It turns out the faster an object moves away from us, the redder the color we see gets. And if we know what color the light starts at, we can calculate how fast the object is moving away from us.
Sort of like taillights on a drunk driver speeding away from a cop. It's getting redder and redder! He's going so fast! Okay, I get it.
So we can tell that the universe is expanding because of the way the far, far off galaxies moving away from us. And what Perlmutter and his collaborators did was they looked at a certain type of light-emitting object called the supernova type 1a. The moral of the story is it's a really bright flash, and we know what color it is. And from this, he could tell how fast these really, really distant galaxies were moving away from us. And from this, he constructed a history of how our universe is expanding. And it turns out that it's accelerating in its expansion. And then he used a cosmological model in Einstein's theory of general relativity to figure out how much of the different types of matter there are in the universe. And what he came up with was astounding because it turns out that you need to include dark matter in the model to be able to describe the evolution of the universe. So the moral of the story is that on all of these different scales that are, larger than the solar system, whether it's doing cosmological tests to see how the universe is evolving, or smaller neighborhood tests where we look at galaxies evolving or galaxies rotating around one another, we can't describe what we're seeing without including a lot of dark matter to account for the missing gravity.
I was going to mention something about just trying to simulate the universe. So how all of the galaxies are distributed throughout the universe is dependent on what the components of the universe were after the Big Bang, and then how they went to evolve and how they collapsed to form stars and galaxies. So if you have any more than 25% dark matter, or if you have less dark matter than 25%, or depending on what that dark matter actually is, if it's normal stuff or if it's some sort of exotic substance, that will then tell you how efficiently things can collapse and start to form galaxies or start to form stars. So they use 25% of dark matter in a certain state, what they call cold dark matter. And based on that, they can recreate through computer simulations what types of galaxies are around and actually where they live and how close to each other they are. So the overall distribution of all the large-scale structure in the universe. So that's a very good test of saying, yes, there's this dark matter. It's made up of this cold stuff, and it makes up about 25% of all the stuff. So almost all of the simulations of how we create the structure in the universe are based on this assumption. So that's another tying observations into computer simulations for concluding that there's this much dark matter out there.
So we've talked a lot about stuff and things. Does anyone have any theories on what this stuff is, where it came from, why we can't see it, what it's going to do, why we should be terrified or not terrified, depending on whether this stuff is nefarious or has evil intentions, or...
That's a great question. So there's two obvious answers to the question. The first obvious answer is it might just be stuff made out of regular material, patio chairs, and whiskey bottles that's just kind of clumped up, and we can't see it because it's not emitting light. It's not a star. And the other theory is that maybe it's some type of particle that isn't interacting with light at all. So these are the two theories. One of them is called the MACHO theory, which stands for Massive Compact Halo Object. And that's the theory that says that maybe there's just a lot of really big Jupiter-sized objects, brown dwarfs, things that are not luminous. There's no nuclear fusion going on, so they're not radiating light, but they're floating around in the universe.
So they're like extinguished balls of crap.
Yeah, it's just balls of crap floating out there. And then there's another theory that says that maybe it's just large clouds of particles that we can't touch, little ghostly particles. And that's called the Weakly Interacting Massive Particle Theory, or WIMP. From basic principles, it's either stuff that we've never heard of, or it's just balls of crap that we can't see. And so in the Massive Compact Halo Object, the MACHO theory, they started looking out in the universe for gravitational lensing. Because if the universe is full of these giant planets that aren't radiating light, then we should see them passing between us and the stars in the background. And occasionally, if you see one pass just between us and one of these background objects, you'll see the luminosity of the background star spike and dim. Just like one of those beads of water passing between a street light as it rolls down the window.
Yeah, they were just looking out from the center of our galaxy. And so when you look out towards, say, Andromeda or some concentration of other stars, and you see one of these dark things passing in front, then you should see some brightening of all those objects in Andromeda or, say, one of the Magellanic Clouds. So they just surveyed regions in the outskirts of our galaxy because that's where we see a lot of this dark matter, a lot of these dark objects.
Yeah, so if you watch night after night, chances are one of these stars will have something passing between it. And the number of times you see one of these massive compact halo objects passing between us and a star should tell you about how many there are. You can do a statistical analysis. And when they did that, they found out that there was only 5% of the amount of mass required in all dark matter. In other words, they found them, they are out there floating around, but there isn't nearly enough of them. You'd need 20 times their number to describe the source for dark matter.
So both theories are plausible, or both added up together might account for all of this undocumented, invisible stuff.
Right. So it looks like the WIMPs won the day. Yeah, most of dark matter, by far, is composed of WIMPs.
Revenge of the Nerds.
That's right.
So under the WIMP theory, I could totally fly a spaceship through it, but under the MACHO theory, that would not be a good idea.
Yeah, it's like a locker room. You know, if you walk through a locker room full of macho guys, you're going to hit one of them. Whereas if it's just full of wimps, you can pass through and nobody will say anything.
Especially if you're dressed as an astronaut.
Yeah.
It's much harder to get through a football team's locker room when you're in an astronaut costume. I have discovered, at any rate.
Or as a super scientist, I have to say.
But wait, in this analogy, there's a constant mass of people. So there would be like one jock and maybe like 20 wimps.
I guess one idea is that you can keep running through a locker room full of wimps and nothing will happen.
That's true, yeah.
Whereas if you keep running through a locker room with one macho guy, eventually he's
going to punch you.
That's right.
Right, yeah. Because the wimp is the weakly interacting massive particle, so the wimps just back away. They don't ever interact with you at all.
So how did they test the WIMP theory?
Yeah, it's more of this is in progress. How are we testing the WIMP theory? Because, I mean, nothing's been found yet. but it's a really hot topic right now. There's a lot of experiments all looking for these WIMPs. So the way that they look for it is these WIMPs are weakly interacting. So they don't interact very much, but every once in a while they do. And there's a lot of them going through the Earth at any given time. So if we get a detector which is sensitive enough, we can actually see these really rare interactions, and we can detect them and then say, there it is, there's your dark matter, and win the Nobel Prize.
So when we say it's a weakly interacting particle, it's not a vague descriptor. It's actually a very specific description. You've heard that there are 4 elementary forces in nature. There's gravitation, electromagnetism, so electric charge and magnets, and then there are 2 nuclear forces. There is the strong force, which binds nucleons in the nucleus together. And then there's the weak interacting force. And the weak force, it's kind of a repulsive force inside of the nucleus. Sometimes it causes radioactive decay. So when we say that these particles are weakly interacting, what we're saying specifically is that they only interact with other particles through this weak interaction. They don't have any response to electromagnetic radiation. They're neutrally charged. And that's why they don't block out the light in the galaxy, so we don't see big clouds of them the way we see clouds of hydrogen. And they don't emit light.
And that's why we have such a hard time detecting it, because they don't just land on our detectors like regular photons from the sun do. So we have a really hard time trying to harness them and trap them and count them and figure out what the heck they are.
Especially because they're going through our Earth all the time.
Yeah, hundreds of billions of these things, of neutrinos from the sun, are just passing through our bodies and Earth all the time, without us noticing.
But let's be careful to separate neutrinos from dark matter.
Right. So neutrinos are a type of elementary particle that gets emitted as a result of nuclear
reactions.
Decay. Yeah, nuclear reactions. So the sun's emitting a ton of these, and we detect them on Earth all the time. There's the Snow Laboratory in Sudbury. There's the Super Kamiokande detector in Japan. So there are detectors that detect neutrinos a lot all the time. How do we know that dark matter isn't neutrinos?
There's several reasons, I think. One of them is that now that we're narrowing in on what the mass of the neutrino actually is, there just aren't enough to make up the density of dark matter that we know exists. And another one is because neutrinos are relativistic. Amanda probably has to speak to this, but if I understand, if all the dark matter was relativistic, it would have washed out structure formation. We would never actually get anything forming.
Exactly. It'd be too hot. You wouldn't be able to have particles get cool enough so that they can actually start to condense and form stars.
So in the WIMP theory, the idea is that there's some unknown elementary nuclear particle that was present in the early universe when everything was really, really hot before nuclei started forming. These elementary particles, so they stopped interacting with atoms as the atoms started forming. And as the rest of the universe cooled, the universe just ended up full of this dark matter detritus. If you give the dark matter too much kinetic energy, it keeps the universe from evolving the way we model it evolving.
Yeah, it can't cool enough to form any of the structure. So you'd never get a galaxy.
Yeah, we wouldn't be here to ask the question.
Well, I'm curious where this goes. I'm wondering what the next steps are. I guess if we're still in the middle of testing the WIMP theory, what are some of the new ideas that people are kicking around for trying to finally figure out a way to measure this stuff?
Oh, there are tons of new ideas to try and figure out how to measure this stuff. So the problem is, like we touched on, these things only interact very rarely in your detector. Most estimates put it like less than 1 interaction per 100 kilograms of mass per day. So you need a lot of mass and stuff to actually detect these things, and you need to let it run for a long time. But the way you detect them is the WIMP comes in, essentially, and just in the brute force kind of way, hits your nucleus of the atom that you're trying to use to test it, and that nucleus recoils. And as it recoils, it deposits energy along the path of its recoil. And then there's a whole bunch of different ways, essentially, to take that really small energy deposit, which is like 10 keV, which is a very small energy deposit, essentially, and magnify it and make it something we can actually see, and then make it something that we can distinguish from background. Like I said, there's lots of experiments right now trying to do this very thing in very different ways.
Yeah, tell us about noble element detectors, Ken, because that was awesome.
Yeah, so that's like kind of the hot new thing right now is these noble element detectors. So you take a big detector and you fill it with xenon, or you fill it with argon, or some are wanting to fill with neon. And essentially, like I said, the particle comes in, it hits the nucleus, it bounces off it, the nucleus skids along, and as it skids along, the atoms along its track get excited a little bit, and then as they relax, they give off a flash of light. So you get this burst of light in your detector. But then at the same time, this skidding nucleus frees electrons, and you use an electric field to drift these electrons through your detector, and then you accelerate them again in a different phase, and you get a second flash of light, and you're able to use these two flashes of light to actually see what happened inside your detector. And if you could see the hand motion I was making right now, it would all be much clearer, I'm sure.
I guess I can't really picture any of the things that you're talking about, so I don't know what the instruments would look like, or the readouts, or the formulas involved. So it becomes a little hard to follow when we're talking about a bunch of different instrumentation. That's my only issue.
Okay, I've got a sweet analogy that gives you an intuitive picture of what's going on, and then I'll make Ken re-explain it to you.
Does it involve bees?
No, it involves mice. So when I lived in Kingston, I had a mouse problem in my house. And the thing about mice is that you're never sure that you have them. You wake up in the morning and there's, mouse poop everywhere, but you never see the mice and you never hear the mice. And so what I did was I put out mouse traps, and they wouldn't trap the mice, but the mice would wander past them, and it would disturb the system enough that the mouse trap would snap and make a big sound and flip out. And so from the mousetrap flipping when it did, I could tell that I actually had mice. There was actually something moving through setting these clappers off. So the principle in this is the same. You set up a system, and then if a WIMP is aimed just right at a nucleus, it won't just pass by it. It will kick it as it's passing. And so you set up these systems, and they're very sensitive to changes, so that when a WIMP comes through and it kicks one of these atoms out of the way, you can see it. It causes a flash of light.
And one day you come back and there's just a tiny paw and a little trail of blood, and you feel like a bad, bad person.
Yeah.
But maybe Ken could explain how that analogy works in the hunt for dark matter.
So that's an interesting analogy, but the real problem is, how do I extend your analogy? In the middle of the night, there are a lot of cats that come by and set off your traps. And it's really tough to tell when a trap has been set off by a cat or when it's been set off by the mouse. And there are way more cats than there are mice. So the real problem that everybody has in the dark matter game is trying to separate the cats from the mice. And what that translates to in the real world, if we can please stop dealing with this analogy, is there's a lot of background. So in these detectors, they're built out of material, right? Most of them are just big tanks of material. For example, a big tank of xenon. And everything the tank is built out of, and the xenon itself, has radioactive particles in it that can mimic your signal. So the real game is not making a detector that can detect things. We're pretty sure we can do that. But the real game is trying to tell what was caused by a WIMP from what was caused by a background event. And that is the really hard part. And that's what everybody's spending all their time and energy on.
Those false alarms.
Exactly. And the false alarms are orders of magnitude more prevalent than the actual signal. Mostly because we've seen a lot of false alarms, and we haven't really seen a signal yet, for the most part.
My brow is furrowed.
Okay, what's up?
Well, I guess I'm still trying to figure out, we're in the middle of this, we're in the middle of testing the WIMP theory, and we're pretty sure that there's both brown dwarves kicking around that account for maybe 5% of this extra matter, and then there's still a huge amount of stuff that we still haven't really been able to capture or identify or get a real reading on or measurement of. I'm wondering, is it kind of like the tree falling in the forest when no one's around? Like, this stuff has presumably been around since the early days of the universe, right? Mm-hmm. So discovering it, I guess I'm trying to figure out what the practical applications are of this emerging knowledge. Why does it matter that we're surrounded? That wasn't a pun. Why is it significant that we're surrounded by all this stuff if it doesn't interact with even itself very much, let alone us? Does it change how we model the future of the universe? Does it change how we understand the solar system in which we live?
That's a great, I mean, the practical application question is the greatest question and the toughest one to answer. I would say that a lot of dark matter, at least from my point of view as an experimentalist, a lot of dark matter is really science for knowledge's sake. You're right. I mean, this stuff has been around for as long as the universe has been around, and it's going through us all the time. It really doesn't have an effect on us. But we really want to know. We want to be able to characterize everything and understand the universe. To my mind, it's really hard to predict what comes from any of this. The more that we know, the better we can predict things for the future.
Right.
And also in terms of simulating what the universe is, on a large scale, just understanding the distribution of where galaxies are, we do a pretty good job. But there's still things like, from the southern hemisphere, you can look up and see the large and small Magellanic Clouds, these two little dwarf galaxies that are gravitationally bound to our Milky Way galaxy. But inside of our models, we have a really, really hard time being able to predict the existence of these things. So in a typical model, we actually predict too many. So we have a hard time predicting exactly the small and large Magellanic Clouds, but overall, the Milky Way system should have something like 60 of these small little things, but we just don't see them when we go out there. So these tiny little dwarf galaxies are completely dominated by dark matter. And since we can't really observe it, and we can't figure out any way to understand what it is, we have a hard time incorporating that into our models. So the big question of how we got here, how the Milky Way is here, there are a lot of details that we don't understand, and a lot of it comes from how dark matter actually interacts.
Yeah, so that about settles it up. So thank you, Ken. Thank you, Amanda. You've done very well, and you've pleased me. Your efforts have borne fruit, and that fruit is sweet. Amanda, you get a coconut.
Oh, if only I could get into it.
And Ken, you get a little baby mouse paw to eat.
Oh, delicious.
So I'd like to thank my guest, Kai Nagata. Thank you very much for coming on.
Hey, thank you for, forcing me out of my comfort zone and bringing me on the show.
I think you did a wonderful job asking questions, and I wish you all the luck in the future. So, listeners, you can email us if you'd like to contact us at barn@titaniumphysics.com, or you can follow us at Twitter at @titaniumphysics. You can visit our website at www.titaniumphysics.com, or look for us on Facebook. If you have a question you'd like my titanium physicist to address, email your questions to tiphyter@titaniumphysics, that's TIE Fighter. And if you're a physicist and you'd like to become one of my titanium physicists, email physics@titaniumphysics.com. We're always recruiting. Feel free to leave a review on iTunes Reviews as well. It helps people find the show. The Titanium Physics Podcast is a member of Brachiolope Media. If you'd enjoyed the show, you might also enjoy Science Sort of or the weekly Wienersmith. Check them out. The intro music is by Ted Logan and the Pharmacists, and the end music is by John Vanderslice. Good day, my friends, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
Didn't Yoda already figure this out on Dagobah like 800 million years ago?
But the citation was lost, so it doesn't count anymore.
But is this what Yoda was talking about? Is this the Force?
No, it's weak. The Force is strong. At least in Luke Skywalker.
And his sister.
Right.
Can I ask a journalistic question, Ken?
Yeah, absolutely.
I'm just curious who's funding all this research.
There are lots of people funding this research. In the U.S., both the NSF and the DOE are funding the research. In Canada, NSERC is funding several different ones.
Is the DOE the Department of Energy?
Yes, yeah.
Okay. So
if we're in Canada,
basically
there's a number of
government.
experiments. Yeah, government. The government funds this stuff. I mean, there's no private funding for the most part.
And is the involvement of the Department of Energy any indication that they expect some kind of a return on the research in terms of solving America's energy crisis, or is this just the most convenient administrative organ to disperse the funds for knowledge's sake?
That is a great question. Essentially, it's just a way to disperse funds, more or less. The Department of Energy gets involved in some pure research areas, and this happens to be one in which they have gotten involved.
So we're not seeing any interest from the private sector, you said. We're not seeing any interest from the Pentagon. We're not seeing any interest so far from the from NASA. It's coming from the DOE.
Yeah, I mean, it would be tough to... I mean, some of these things would be great, right? If you could figure out how to make an engine that that is powered by dark matter, I guess you could probably get private interest. I suppose the Pentagon would be interested if you could weaponize it somehow, but I think that's probably and hopefully impossible. But for the most part, yeah, it's just government research funding that's actually going into this stuff.
And is that funding stable, or are you having a harder and harder time? Amanda, you were talking about justifying your research when you're applying for grants. I'm curious whether in Canada, Australia, the States right now, it's a bright future for pure science research, or whether people are worried about losing their funding.
Oh, people are most certainly worried about losing their funding. Absolutely. And it's gotten to the case now where essentially there are many ways to do the same thing. For example, with the xenon detectors, there are several different xenon projects, but governments now are kind of saying we're only going to fund one. We're going to fund the one that looks the best, and everybody else is out of money. So it is tight right now. I mean, money is obviously scarce.
Yeah, that's absolutely an issue. And for the particle physics experiments, they are really expensive. So there's not a whole lot of private funding that can really occur to fund those things. I know the LHC in Europe, I mean, there are lots and lots of different countries on a national level that are contributing to that. But if that's all of your research science budget, maybe it comes away from something else, like from some astronomy telescope or something, in order to keep up your end of what you've agreed to contribute to this big experiment.
Yeah, I was just curious. Thanks for giving me the picture on the research scene, because I happen to know some researchers in math and physics, and they've found that there's been a politicization, basically, of how the money goes out depending on what you're working on. So I was curious.
That's true. You always want to put in those exciting buzzwords in order to get people excited about it, regardless of what the details are that you do. That's just kind of the game that you have to play, I think.
And I think particularly in the dark matter field, I mean, it has a couple advantages. It's a pretty sexy field right now. There's a lot of interest, but also there's competition with other countries. Other countries also have dark matter experiments, so you don't want to let the other countries get ahead, essentially. So you're able to play that sort of thing to get a little bit more funding, but it's still, Amanda's right, this is expensive physics that we're talking about here, so the money is not easy to come by.
Wow, let's hope the Russians don't launch a dark matter Sputnik. We're all going to feel really, really ashamed. Cool. Sorry, back to you, Ben.
I thought that discussion was fantastic, and I might leave it in here, frankly, because I don't think you should be able to separate politics from basic research, especially if basic research derives so much of its impetus from public funding, and they have politicized it. So I might leave the discussion in just because that's a message I want to get out there.
I'm also a member of the paying public, and I actually, the same way I think that opera is awesome, I like pure physics research, and it actually doesn't bother me, along with like potholes and hockey arenas, to fund scientific research. I think that's a really cool use of tax dollars. But I also like having it explained one-on-one by some of the leading minds in the field, so that I sort of get a sense of why people are excited about it. And knowing the funding picture is actually, I think, pretty interesting as a citizen, as one of the people who's actually paying into the government funding bodies that that in turn pay for the research.
Okay.
And the one thing that I would add then, just not to continue this too much longer, but Canada is in a great position because they have the Snow Lab facility. There's a number of dark matter experiments that are going on in there right now, and it is effectively the best facility in the world, and it's been entirely funded by several different branches of government, but NSERC and FedNor and a number of other branches have come together to make this really the best place to do underground physics in the world. So that's just my plug for Snow Lab in general.
Sweet. All right.